Alright, so today in this video we're going to talk about forces on curved submerged surfaces. Alright, so we'll just write curved surfaces to save time. Alright, so the difference here is that previously we had the idea, we had our surface, our liquid, and our surface was flat, right, and made some known angle alpha. All right, so now the difference is going to be this. Instead of having a flat surface, we're going to have a surface that has some shape to it. That's too shapy. All right, so there's some curvature to the surface. All right, and let's say I'm interested in maybe this region. It doesn't really matter, but some region of a surface where the surface is curved. All right, and I want to know what the force due to the hydrostatic pressure is on that surface, just like I did with the flat surfaces. And the difference here is that previously, if I was just, let's say here, at some arbitrary height, right here, so we'll just say h, and I look at this little pretend area that this thing is acting on, if we call that dA, that's the surface, and if this has an angle theta, then this would be dA sine theta, all right, and we could call this dAx, and this surface here, which we could call dAy, would equal dA cosine theta. All right, meaning that this little surface is the little surface that's at this point h. All right, and I could, if I broke it down, think about these two surfaces in this way. All right, now we know already that the pressure at this little point is P, which would equal rho g h. Right. Now, if we think about P, it's going to be this right here, right? P, and the key part about P is it's going to act normal to the surface, right? Pressure acts normal to the surface, which means that really, if this is the magnitude of P, right? This is the magnitude, then we could really think about breaking P down into a vector and say that there's some P cosine theta in the I direction, all right, plus P sine theta in the J direction, just at this point, all right? Again, all of this is assuming sort of at this little point, all right? So I could say that what's my force? What is the little force on dA in vector, all right? And that would be P dA, all right? And that would end up equaling P cosine, P cosine theta dA in the I direction plus P sine theta dA in the J or the Y direction. Now the cosine and the sine theta, right, all come from this theta here, right? This theta here, which is going to be changing based on where I am in the curvature. It doesn't really matter what the value is, all right? And clearly we're assuming a frame of reference such that, right, this is x, okay, and this is y. And actually, really, if we're going to be specific based on the way I've drawn it, we would say that this is y, so this is j, and this is I. It doesn't particularly matter. All right, so if I look at this, then this cosine dA here, this is actually dAy, and this sine theta dA is actually dAx. All right, and so we could come over here and say that this dF dA equals P dA in the I direction plus P dA, dAy in the I direction plus P dAx in the J direction. Right? And you could actually say that this is dFx and this is dFy. All right, now we're going to think about dfx and dfy separately because they're easier to think about separately. All right, so the first thing we're going to do is think about dfy. All right, so we have dfy. All right, and what we really want to know is what is fy. All right, so instead of dfy, let's erase that accidentally. What is the total force on this curved surface? Well, it's fy is going to equal the integral over my surface of dfy. All right, and then we could say, so that's the integral over my surface of p times dax. Remembering, I'm sorry, yeah, dax. Remembering from before, so like I said, remembering from before, if we go back to our original picture, here we have dax right here. It's that horizontal area projection, and day is the vertical area projection. Okay, so here we have p dax. Okay, and we could rewrite this again as the integral over my surface of p, which is really rho g h, all right, times dax. Now, let's think about that. Okay, if we have our surface here, and here is da-da-da, and here we are, again, here's our little area we care about, dA, and this is dax, and this is day. All right, and this distance here is h. Then I'm going to move that out a little bit. So this distance here is h. Then what is h dax really? Well, h dax, if you think about it, is this column of fluid right here. Right? It's in fact the volume above that little surface, right? And so we could rewrite this equation then actually as the integral over our surface of rho g. Instead of h dax, we could actually call this what? Well, we could actually call this dv. And when I do volume, I tend to put a little line through it to differentiate it from velocity. All right? And that's because we can see from this picture, right, over here, that really h dax is really this volume. So if I do the integral over the whole surface, what am I really saying is if I'm integrating over this whole surface, right, and here's my surface, then when I do this, right, what I'm really saying is if I integrate over my whole surface, I'm really thinking about this volume, right, which is what? This is the volume above my surface, which means that the force in the y direction is really rho g v above. Okay, so this is really the force in the y direction on a curved surface. We're going to break it down like this. Is basically the force of the weight of the water above the surface. Okay, that is very simple. Okay, force of the weight of the water above the surface. All right, now let's think about what is Fx. Again, we're going to start from the same idea. So what's the total force in the x direction? Well, it's dFx, the integral over the entire surface. All right, and so this is, again, the integral over my entire surface of P day. All right, now let's think about our picture again. Here's our surface. Here's our curvature, and it goes like this. All right. And if we're looking at this little thing again, right, day is this little area. It's this projected area onto the y-axis. So for every point where I measure, right, I'm going to be taking this little projection onto the y-axis. So what happens is if I think about what this integral is really doing, really what I'm doing is, and at any particular, so here's my h, right? And here's my day, and then here would be an h, and then here's my day. And really what this looks like is the h And the day, if that's just sort of a planar surface, really what this looks like is I'm looking at the force on a flat surface that's perpendicular to my water. All right, and so what we do is we keep writing this out, the integral, I'll pull out the rho g, and then you have h day. Well, effectively, over my whole surface, effectively, this series of days over here is a planar surface, okay, with a theta, or an alpha, was what we used before, equal to 90 degrees. So effectively, it's kind of like this, okay, and this is my day over there. This is my entire projected surface. All right. So if you think about it that way, then this h is really the y from our planar surfaces. Okay, so you can really keep thinking about this then as if this is my planar surface, then some height here, right? This is my height h. Okay, then if this plane is a planar surface with an angle of 90, then h and y are essentially the same thing. All right, and so we have our equals the rho g, so here's fx equals rho g, the integral of h over my surface day. Well, I could rewrite this as to be equal to, say that my centroid, right, is equal to 1 over the projected area, the integral, over my projected, and instead of s here, let's write ay over ay of h day. All right, and then I could combine these to essentially say that the force in the x direction is equal to rho g, the height of the centroid of the projected area, times the projected area. Okay, now sometimes people don't like this projected area. It confuses them, so let's draw a little picture to help us figure out what is the projected area. All right, here's my curved surface. It's curved in 2D only, meaning it's got this curvature, but into the depth of the paper or the board or the computer screen, it's just doing this curvature all the way in. It doesn't have to. There can be, it can be circles and things like that, and we'll show examples of that. All right, then the projected area, again on this, here's my j, all right, and here's my x. All right, then the projected area is going to be the area here. All right, this is ay. And to think about it is to think about what would happen if I was standing, I'm going to draw this giant eyeball. What if I was standing right here and I looked at my curved surface? What would it look like to me? Well, if it was a planar curve, meaning that it was just this curve, depth into the board, what would this look like? Ay would be a rectangle, right? With whatever depth my curved surface had and whatever final height this was. So let's call this h0, all right? h0, all right? That would be the depth. What if I was looking at a surface, it was a little different? What if, say, I was looking at a surface and, I'll draw it in black again, sorry. It was, here we go, drawn in black. And it looked like this, and I tell you, this is a half a sphere with a radius of r. What would that look like if I was looking at it from here? Well, the projected area would be a circle with a radius of r, right? So it's the idea is you look at it straight on, what would you see if you didn't see any angles, and that's the surface you would see. All right. So there's one more thing we need to talk about. So now we have, all right, we have fx equals rho g v above, and fy equals the pressure at the centroid of the projected area, which is rho g h centroid of ay times ay. All right. Where do these act? Okay. This is easy. Okay. The x value here, you can say that this acts at HCP, which is equal to IXX hc times a. So essentially, the x force on the curved surface acts at the height of the ay. Sorry. So let me add in a few details here. The force in the x direction acts at the center of pressure of the projected shape in the AY. So again, if you have a square or a rectangle, then you would calculate the HCP of the rectangle, and that's where the projected shape, the force acts. All right. Then this acts at the centroid of the volume above my shape. So let's say, here's my shape. Let's do something simple, a curve that's like this. And I've asked you to find the force on this curve here. If this is my area, I would calculate its centroid. And I would calculate its centroid. So if this is x and this is y, I would calculate not its y centroid. I don't care about that, but I care about this distance here, which is xc. And so xc equals 1 over the area, the integral of x dA of this particular area. And the limits of integration on this are a little tricky, but you can figure it out. The lower limit of integration, particularly in the x direction, is going to be defined by this curve, right? Okay. So what's really interesting about the curved surfaces is this, that we can use forces on curved surfaces to think about buoyancy. And that's the sort of the final gist of this chapter. So we're just going to think about a shape like this, a sphere underwater. So let's say here's the center of the sphere R, and it's at some height d underwater. All right, so there's not going to be any x forces, so Fx is going to equal 0. Why? Because it's symmetric, all right, and pressure acts normal. So you can prove that yourself, but essentially if I have a pressure here and the pressure here at the same positions, the x pressure, right, the pressure in the x direction, cancels out. All right, so now let's figure out what is the y force above and below on this thing. So the way to do that is to actually break this up into two problems. We're going to split the sphere in half, and we're going to think about a surface that looks like this, that's that sphere, and then a second surface that is this. All right? And so for the first surface, the volume above is this volume. And for the second surface, the volume above is this volume. Right? So we'll call this volume 1, and we'll call this volume 2. All right, so force 1 is rho g v1. All right, and that equals what? Rho g, well, what's v1? v1 is pi r squared times d minus 1/2 pi r cubed. Okay, because there's basically a cylinder there, and it's minus 1/2 4/3 pi r cubed. Sorry, doesn't really matter. All right, there's 1/2 of the cylinder. There's the cylinder there, and I remove the bottom half of the sphere, right? And that force is actually negative, right? It's acting down on the surface. All right, force 2 is going to equal rho g, and what's that volume? That's also got that pi r squared d, because there's that cylinder. This time it's plus 1/2 4/3 pi r cubed, because you add that. And these two forces, in fact, this is positive, this one's pushing up. So this is force 1 would be down that way, and force 2 is up that way. So the net force on this thing, sum of the forces, is going to be force 2 plus force 1. And if I add those together, what happens? All right, what happens is you get the pi r squared d's are going to cancel, and so what you end up getting is rho g 4/3 pi r cubed, or rho g, okay, times the volume of the sphere. All right. Now that is the force due to the liquid pressure. Now, how do we know if something floats? Well, we could calculate the buoyancy force. All right. So this is essentially what we call the buoyancy force, right? So that's it. It's the volume of the object, and this is the density of the liquid. So if we wanted to know, does something float? Let's say sum of forces in the y, the buoyancy force minus its weight. All right. And this is rho liquid g times the volume of our object minus rho of our object, so we'll say solid, g, and its volume. And that's where you get that problem where you'll say that sometimes in physics you might have learned that the buoyancy force is actually delta rho g v. All right, but all of that, the buoyancy, all of buoyancy comes from this idea of forces on surfaces, and that it's just hydrostatic pressure.